Good afternoon. I think you have a good time during the lunch hour. My name is Ishi Shin, professor, Incheon National University, South Korea, and also I'm a vice president of ICSMGE for Asian region. It's a special privilege to be a chair of this session. Welcome all of you to the session called State of the Art Lecture, Biomediation, Bio-inspired geotechnics. We have two speakers, as you see on the screen. First speaker of this session, Professor Jason DeJong, professor at the University of California at Davis. He obtained a BS degree from the University of California, Davis, and MS and the PhD from Georgia Institute of Technology. He has a working experience offshore foundation system at the University of Western Australia and also University of Massachusetts at Amherst. He has been awarded $13 million granted from so far from all of the different agencies, and also 200 paper publication. He has been received numerous awards from the ASTM, ASCE, and also he received Sansa Prakash Award. And let me introduce the second speaker of this session, because they continuously talk, without a break. Professor Michael Gomez. I think you got to stand up, right? So people are aware who you are. Yeah, thank you. Yeah, Professor Gomez is assistant professor at the University of Washington, Seattle, and he obtained a PhD from University of California, Davis. His research focuses on the chemical and the biological process in soil, and the bioremediation, geotechnical ground improvement technology. He focuses on the strength of loose and soft granular soil through the biotreatment, calcite precipitation, we call MICP. Let me introduce first speaker, please, DeJong. Give him proud.
Well, hello, colleagues, both in person and remotely. It is certainly a pleasure and an honor to be able to present with Mike Gomez the state-of-the-art presentation in biomediated and bio-inspired geotechnics. The title of the paper and the title of the presentation, as you can see on the screen, is MICP Soil Improvement and its Application to Liquefaction Hazard Mitigation. We certainly want to recognize the co-authors listed on the screen, as this was very much a team effort, as well as in another 20 to 25 colleagues who we communicated with to obtain and incorporate data, references, and other projects. We're from a number of different universities, but we are largely affiliated with the U.S. Center for Biomediated and Bio-Inspired Geotechnics. And so let's go ahead and get started in the presentation and walk through this. First of all, just an introduction and looking at things from a very wide and broad view. You've perhaps seen schematics such as this one's or other ones in literature, which are trying to communicate to a broad audience some of the vision we see in biomediated and bio-inspired geotechnics. Some of the elements you see are familiar in shape, perhaps different in composition. Other ones are familiar at their application, but are different in shape, indicating some of these different ideas. But very broadly, we could say that the field of biogeotechnics is rooted in the hypothesis that studying, understanding, harnessing, translating, and applying biological processes and ideas can stimulate innovation and generate new geotechnical technologies that will produce a step change in geotechnical practice with respect to sustainability, performance, safety, and ultimately societal well-being. So we're very familiar and well-versed in providing performance and safety. We're coming along with respect to sustainability, so I just want to make a few brief comments in that regard. And the first is I believe that geotechnical engineering as a whole has a role and a significant opportunity to contribute directly to the United Nations Sustainable Development Goals. A review of these 17 objectives, I think you could draw that about 10 of them we could have direct influence on, and the other ones perhaps indirectly. To do that, we require some systematic framework, such as life cycle sustainability analysis, that will allow us to quantitatively evaluate the sustainability of these new technologies that we're developing and compare them to the business-as-usual technologies that our industry already uses. But there's tension in this, and I think the Collingridge dilemma highlights this tension adequately. And that's shown in the bottom right hand of your screen. You can see on the x-axis is project maturity from an infancy to final field implementation. On the left vertical axis is the potential for change in your design, and the right axis is the cost for that change in design. And early in project maturity, we have wide flexibility. We have the opportunity to exchange parts to improve our design, but we actually have relatively limited knowledge of what is necessary in our idea and what is optional in the idea. But later on, the opposite is the case, in that our solution has now become pretty constrained and defined, and now change costs a lot and is impactful. And so as a result, I believe it's important for us to be evaluating how sustainable these new ideas may be relative to current practice throughout the technology development process. Now, more broadly, we could probably break out this whole area of biogeotechnics into two categories. The first being biomediated technologies, which has really seen an influx of activity in the last 20 years or so. And in this way, I'll define it as the initiation and regulation of natural biogeochemomechanical processes to produce step changes in engineering soil properties. And really, our objective is to realize some type of chemical reaction, most likely in the soil matrix, but this is mediated by biology, controlling the timing, rate, and distribution of where these reactions take place. We want to realize our objective of mechanical changes in those properties, but we need to monitor the process along the way, and we'll discuss that. We need to push to the field, and one of these topics or potential applications is liquefaction, which we'll focus on a bit today. And in that upscaling, we have challenges with respect to uniformity, permanence, and byproducts as well. There's a whole host of these different technologies that are in the literature and are being actively pursued: biocementation, biogas, biofilms, and you'll see various combinations of these different technologies as well. And people's vision is that there are a wide range of applications that these could be used for, and this will be demonstrated in due time, I believe. But some of the upscaling challenges we're actually somewhat familiar with both with respect to current ground improvement technologies and some of the bioremediation methods that we already use. More recently, bio-inspired geotechnics has become much more active in the last 10 years. And in this case, we're looking and studying biology and trying to abstract and translate something from a natural biological system to develop new solutions to engineering challenges. And this workflow diagram looks a bit different. Here we'll begin with a study of a biological system in terms of, we'll integrate that with our engineering knowledge as practitioners and try to couple those two to develop and to abstract different ideas from biology that could have benefits for us as engineers. We're going to formulate hypotheses at that point of what might be possible. We're going to end up testing those hypotheses, maturing along the way, and we're going to be then trying to upscale these to field as well, because that's our end objective, is to help improve and benefit practice. And ultimately, we will have realized in the field some new sensor or some improvement technology or something else. It's obviously an iterative procedure. These are hypotheses that need to be tested and refined to progress forward. And there's a host of examples in this field as well. 3 examples I'll highlight here: snakeskin-inspired anisotropic surfaces, or anisotropic friction, peristaltic self-reacting probes to help advance probes into the field in nonlinear directions, and different root-inspired 3D anchorage types of systems as well. Now, a comparison of existing natural biological systems and some of the systems we design indicates that there is potential for up to a 10 times improvement in terms of normalized performance with respect to either volume or mass. But we have upscaling challenges here too, particularly with respect to the stress regimes that we're talking about and the length scales that we're talking about. Now, as we were asked this and then started preparing the scope of our paper, A review of literature would show that there have been about 25 reviews written on these two areas just in the last 3 years. So a lot of people have provided a lot of high-level overviews, some in our main journals, some in our peripheral journals. And so we felt that that literature and those examples are out there. So our interest and our focus for this paper was instead to demonstrate and to show the depth and rigor that we believe can be realized in this biogeotechnical realm also. So in doing so, we selected the MICP technology, and that's what we're going to talk through. The numbers correspond to the sections of the paper as outlined here. And the hope in this is that we have provided enough documentation of the state of the art such that this becomes accessible and usable by people in practice and researchers who are interested in engaging in the field. So Mike Gomez is going to present sections 2, 3, and 4, which is simply what is the science, how can we engineer or control this, and how can we monitor it? And then it'll be turned back to me, and I'll walk through the types of changes we're seeing with respect to engineering properties and talk about 2 aspects of upscaling before drawing a few conclusions. So Mike, here you go.
Thank you, Jason, and thank you all for the opportunity to present today. So now we're going to transition to discussing the MICP treatment process, in particular talking about the fundamental science underpinning this technology. Microbial-induced calcite precipitation is a biomediated cementation process that is enabled by microbial ureolysis in the presence of calcium. The process results from a series of reactions, the first of which is the hydrolysis of urea by ureolytic microorganisms, which form ammonia and carbonic acid. The net result of all of these different reactions is that there is a net generation of carbonate species, and we can enable supersaturation of pore fluids with respect to calcium carbonate minerals and induce calcium carbonate precipitation both on soil particle contacts and at soil particle surfaces. Although other processes could be used, the choice of ureolysis is quite prudent in the sense that it affords precipitation rates that can be 1 to 3 orders of magnitude greater than that which can be obtained with other redox processes. There are several ways to activate ureolytic activity for MICP. Augmentation was the first approach that was used and involves the introduction of ex situ cultured exogenous or non-native ureolytic bacteria. While the process is effective, it certainly has its limitations, including issues with spatial uniformity due to the fact that cells get filtered out through colloidal filtration when injected in porous media. This, in turn, concentrates cells near injection sources, and it also has challenges with respect to environmental impacts, in particular the materials and energy required to deliver these cells at sufficient densities to various project sites. Stimulation instead, however, is the use of selective substrates, and it's our preferred approach, and it involves the enrichment of existing native soil microorganisms in order to complete this process, specifically the capacity to hydrolyze urea. The process is frequently used in bioremediation applications and has the potential to improve the spatial uniformity of biocementation, requiring only the transportation of soluble reactants throughout the pore space. This translates into significant potential for environmental benefits, as well as reductions in materials and energy required to complete this process. Furthermore, ureolytic bacteria are ubiquitous in geotechnically relevant soils. They play an important role in nitrogen cycling in natural soil systems, and so this process is highly feasible in a variety of different soil materials. Soil bacterial communities change during the MICP treatment process, and we can specifically track changes related to the augmentation of non-native bacteria and the stimulation of native bacteria during this process. Specifically, we can do this with 16S RNA sequencing, which allows us to capture these changes in time, such as the data set shown here for stimulated soil, using both a combination of sequencing on isolates and subclones. In this specific data set, what we're really looking at is the soil being enriched for approximately 4 days and then cemented for 10 days onward after that. The sequencing data here shows some interesting results, first of which is that the stimulated bacteria are closely related to the augmented Sporosarcina pasteurii strain. Secondly, there's also a great diversity in the range of different strains and bacterial species that are actually stimulated in these communities, indicating really that the process is robust, not dependent on a particular soil bacterium being present in a given material, and that really this can be quite successful in a variety of different environments. When we consider similar augmented soils, as we're seeing in the data set here, we can see the introduction of a non-native ATCC 11859 strain. That's our type culture for what we would inject as cultured from the laboratory. We can see that it has a clear signature in the data set in terms of RNA sequencing immediately after introduction. However, there's a steep decline in its appearance after only about 4 days, suggesting that these augmented bacteria can be outcompeted by stimulated or native bacteria, specifically when nutrients are present. It follows that many past studies, although they may have intended to complete augmentation, may have unknowingly involved some amount of unintended stimulation. Although MICP is commonly referred to as generating calcite, mineral formation during MICP is a transient process with mineralogical changes occurring throughout the treatment process. Small-scale tests, such as the one shown here, have involved microfluidic chips in batch experiments and provide direct observations and monitoring of mineral nucleation, growth, and transformations in time, which clearly show progressions in mineralogy. We see the appearance in particular of less stable vaterite and amorphous calcium carbonate, with these crystals or minerals progressively dissolving to form more stable calcite. This can be verified visually through the images which we're seeing here, but it can also be quantitatively confirmed using X-ray diffraction, which can assess mineral presence. Of course, the minerals that are formed during these systems are going to be quite important when we start to think about what is the longevity of this material and how long might it exist at a particular project site. Cemented soil microstructure can be characterized using a variety of different direct imaging and surface characterization techniques. In particular, the precipitation that results is going to generate particle surface coatings, particle-to-particle contact bonding, bulk densification of the soil minerals matrix through the precipitation of mineral solids, and changes in particle angularity through the cladding of soil particles with additional precipitation, all while retaining the open pore structure of the original soil material. Obviously, these microstructural changes map to changes in engineering behaviors, specifically thinking about differences in stiffness, strength, and volumetric tendencies or dilatancy. Microscale mechanism or microscale mechanical testing can really help us understand what is going on at the particle level, and in particular, the role of cementation towards enhancing macroscale engineering behaviors. For example, we can see from 2 particle tensile tests that both the distributions of bonds and their mode of failure can govern behaviors such as initial stiffness and peak tensile strength, with debonding of cementation from particle surfaces affording greater strength than internal failure of cemented bonds. Post-shearing, we can see significant changes in particle shape and roughness afforded by the cladding of those particles with precipitation, and these persist even at larger strains. Direct imaging of those particles can afford quantification of these changes using various metrics, such as sphericity and roundness, such as that shown here in the plot with changes in cementation level. The net result, of course, is the transformation of behaviors at small strains, primarily resulting from particle-to-particle bonding, and at large strains resulting from the soil matrix, which is now densified and has particles that are more angular. Now, a key aspect of any ground improvement technology is, of course, knowing its limitations. In this sense, understanding and evaluating the permanence of biocementation is critical towards identifying favorable field applications, quantifying life cycle environmental impacts, and predicting long-term material permanence and performance. Although not always of concern, dissolution, when favored, is a time-dependent process that's controlled by the solubility of the minerals present, the surrounding groundwater composition and its transport through treated soil zones, and precipitate surface area in contact with that mineral and the dissolving fluid. Reactive transport modeling can leverage some of these experimental insights in order to be able to capture degradation both spatially and temporally. As shown here, a series of soil columns were treated identically and then exposed to 50 dissolution acidic injections, which were applied from the bottom upwards. The data points shown are actually measured from physical soil column experiments and demonstrate calcite contents as a function of distance from the injection source. And the dashed lines shown are Freak-C 1D reactive transport model simulations, which can reasonably capture such trends using existing mineral dissolution frameworks. Of course, these models show great potential and ultimately may be used in the future to help us predict biocementation degradation for site-specific conditions when the technology is ultimately applied at field scale. So let's transition and now talk a little bit more about the MICP treatment process and how it can be implemented from a more practical context, including specific treatment phases and other considerations. Biocementation is accomplished through a series of different treatment phases, the first of which is enrichment or stimulation of native indigenous ureolytic bacteria in order to develop sufficient ureolytic capacity. Once sufficient cells are present and we're able to then initiate biocementation process, cementation can proceed by supplying solutions which contain soluble calcium, which allow for progressive improvements through cementation. As a final step, of course, that ammonium which we talked about in the beginning is going to be removed through the application, in this case, of rinse injections, which can remove these species to levels acceptable to satisfy site requirements. And an understanding of these processes has really resulted in a variety of different changes to the way in which we apply this process. Specifically, this has guided development of preferred treatment approaches, and these formulations are not necessarily static, but rather we understand the process styles to the extent that we can modify treatment formulations for a given engineering performance and application that may be desired. Microbial activity, of course, is one of those process styles. And in this case, what it's helping us do is it's helping us control the release of reactive species and enable the control of precipitation in a manner which is very similar to what we can think of as a gel time for a conventional grouting technology. Enrichment solutions can control microbial activity through targeted ureolytic cell growth, including cell densities and their magnitudes, as well as the fraction of cells which are ureolytic. For all treatment techniques, of course, what we're trying to target here, whoops, sorry, I jumped ahead there. For all treatment techniques, what we're trying to target here is a variety of different goals. We want reliable initiation of the process. We also want to be able to minimize materials and energy required. And we want to be able to control reaction speed so that ultimately we control the cementation distribution in the subsurface. Through the optimization of these solutions, insights have been achieved, which have translated into identification of really effective process dials, as well as the maximization of environmental benefits, which of course is the motivating factor for this technology. For example, the data set shown here is coming from 2 soil column experiments during a typical treatment program. One column received a standard treatment concentration of 350 millimolar urea, while the other column received 7 times less urea. What we see is that upon transitioning to cementation around day 4, something like this, we see that there's no real significant differences in activity despite the fact that we were using 7 times less urea. And of course, we were able to significantly reduce those concentrations and material and energy costs associated with that. Upon transitioning now, we can also think about how we can regulate geochemical conditions in order to carefully control process timing and cementation spatial distribution. We can see, as illustrated in this diagram, which is an activity ratio diagram, we can compare solution carbonate and calcium concentrations to the solubility of calcite mineral, which is shown as the omega equals 1 line, or the solubility of calcite. As shown, after stimulation in this flow diagram, we see that we have high concentrations of carbonate resulting from the hydrolysis of urea, and these can be removed prior to starting the cementation process through flush injections, which aim to remove reactive species and prevent issues such as well clogging. A subsequent cementation injection is then applied and pushes the system out to higher calcium activities. It is then ureolysis that continues to generate carbonate hours after injections, therefore consuming supplied calcium until near equilibrium conditions are achieved between the fluid and mineral phases, and only then does the system become ready for a subsequent treatment injection if it is desired. Following the MICP treatment process, we can also think about the generated ammonium resulting from this process. It can be effectively removed in order to meet site-specific criteria. Removal can be accomplished in a variety of different phases, or using a variety of different techniques, I should say, including advection, microbial nitrogen transformations, or other methods such as electrokinetics. Our current approach uses advection and the application of post-treatment rinse solutions, which have high cation concentrations included in them. As shown, we can track changes in aqueous ammonium exiting the column versus injected pore volume. And we can also track changes in sorbed ammonium concentrations as a function of soil column distance. When comparing different solutions, such as the plot shown here, it's clear that supplied rinse solutions, or rinse solution cations, I should say, can enhance cation exchange of sorbed ammonium concentrations and get effective removal from both pore fluids and soil phases. The net result at the end of this is that we're able to remove approximately 98% or more of the ammonium that's generated at meter scale as well, with minimal impacts to the cementation overall. When considering soil compatibility, MICP has already been demonstrated in a broad range of soil materials. Treatment effectiveness in a given soil is controlled by several different factors, the first of which, of course, is the ability to develop sufficient ureolytic capacity needed to complete this process, the ability to deliver reactants effectively throughout these subsurface regions prior to reaction, and the magnitudes and distribution of that cementation on soil particle surfaces and at contacts. For augmentation, treatability or treatment success is largely controlled by the compatibility between bacterial cell size as well as soil pore size, which can limit cell transport, particularly once pores become exceedingly small to pass cells through. Stimulation instead may extend this range, really requiring only the transport of soluble reactant species, and certainly we think that this might make it more effective in finer materials. When considering the breadth of studies that are out there, what we can see is that there is clear success in a variety of different sandy and gravelly materials, with the upper bound particle size largely governed by practicality and treatment efficacy considerations, and the lower bound particle size largely governed by limitations related to low hydraulic conductivities. What we can also see is that more recently the field has extended into challenging new materials such as tailings and combustion residuals, and of course this is quite promising and exciting moving forward. So now we're going to transition and turn our attention into process monitoring techniques, which can be used to track various aspects of the process, including those related to microbiological and geochemical aspects, as well as methods that we can use to demonstrate and verify improvement once we've completed it. Characterization of microbial activity is a key component of this and to any successful process deployment of MICP. Specifically, one of the aspects that can be monitored is urea degradation, and this is effective means by which activity of the microbes can be determined in order to determine when stimulation can end, when cementation can commence, and how reactive transport conditions can be modified to alter the spatial distribution of the cementation once precipitated in the subsurface. This, of course, can be captured using a variety of different kinetic models over time, and ultimately can be used to provide predictive capabilities when incorporated into reactive transport models. Here we're showing urea degradation trends in time for a given injection period, and from this we can see that the lower complexity zero-order earth models can reasonably capture initial trends observed at high concentrations. However, as we proceed in time, first-order and Michaelis-Menten models can capture behaviors over the full reaction period much better by incorporating information about enzyme affinity and saturation. Calcite precipitation can also be captured using aqueous chemical measurements during the cementation or treatment process. Both urea and calcium can be used to collectively determine the end of reactions as well as injection intervals, with parity between these trends really highlighting the fact that microbial activity is controlling the rate in which this process occurs. After alt treatment, soil calcite content magnitudes and distributions can be assessed directly in order to further understand the level of improvement achieved. And further characterization of this produced calcium carbonate can be possible using things such as XRD and other methods, which suggest that under most reaction conditions, higher stability calcite is the predominant mineral phase generated during MICP. Shear wave velocity can be used to reliably and non-destructively assess engineering improvement with increases in cementation. When we look at data compiled from many different tests on sandy-like soils, we see that shear wave velocity increases in a near linear-like manner from values of about 100 meters per second to something like 800 meters per second as we cement soils up to 4% calcite by mass. Of course, we also see minimal dependencies on initial relative density and confining stress. We can also then plot upscaling experiment results on the same plot. And what we can see is that there's, again, consistent trends suggesting that we can complete the process at meter scale and obtain similar results. And when we add in some of the results from centrifuge testing, of course, what we learn is that VS can provide effective characterization of cemented specimens prior to applying loading events, and it can also track the degradation of cementation during the loading process. Such trends, of course, show only small variations in soil types, fines content, and treatment conditions, and being most sensitive to the variable of interest, of course, which is cementation level. Soil hydraulic conductivity can also provide an indirect measurement of cementation. Changes in hydraulic conductivity are, of course, going to be dependent on several different factors. This is going to include the distribution of calcite within the pore space, the magnitude of calcite, and the gradation and soil pore size distribution of the parent material. Recent hydraulic conductivity testing on cemented sands has really considered a broad range of soil particle sizes and have yielded the following soil structures shown here in these images, which were obtained from X-ray CT scanning. These tests show that even at very large cementation contents of about 20% by mass, we're able to see that hydraulic conductivity is only really reduced by about 1 order of magnitude. This is counter to earlier studies which have suffered potentially from localized clogging and accordingly suggested that hydraulic conductivity reductions were much larger. We can also use a Kozeny-Kármán-based model in order to capture this trend as shown above, where normalized conductivity is now plotted versus the pore volume fraction of calcite. We can see that the exponent n in this particular model can be related to calcite amount and relates this calcite magnitude to permeability reductions. It's quite large when we look at past data sets which likely experienced clogging and varied between something between 10 and 80. However, recent tests have exponents or n values that are near 2 to 6 in better agreement with expected trends simply resulting from densification. Cone tip resistance provides the ability to detect post-treatment improvement through its sensitivity to changes in soil stiffness and strength. As an example, we can look at several soundings completed in materials cemented to varying cementation levels, ranging from untreated in the gray lines to more highly cemented in the dark blue line. These soundings here show an increase in tip resistance at a confining stress of about 50 kPa from something like 2.5 MPa to 22 MPa when we have a moderate level of cementation corresponding to a calcite content of about 4% or a shear wave velocity increase of about 600 meters per second. We can also see that cone tip resistance is somewhat more insensitive at light levels of cementation with a limit of detection near 2% by mass. When we look at results from multiple studies and plot normalized improvements in cone tip resistance versus normalized improvements in shear wave velocity, what we see is that these results are consistent between studies independent of confining stress, treatment variations, et cetera, and both metrics are able to be effective across all of these different conditions. We also see that there's initially a flatter slope in this trend at low calcite content, suggesting that while cone tip resistance is quite effective at understanding these higher cementation levels, shear wave velocity really remains a more sensitive and effective tool when we have very light levels of cementation. The use of both shear wave velocity and cone tip resistance measurements in tandem, however, are quite powerful and can even further improve cementation detection. Soil microstructural effects can be identified using an empirical Kg parameter, which accounts for the anticipated effects of relative density and confining stress on cone tip resistance and small strain shear stiffness, allowing for cementation, of course, to be more effectively detected. The Kg parameter, in effect, considers whether or not a soil stiffness to penetration resistance ratio exceeds expectations for a given soil relative density as expressed by a stress-normalized cone tip resistance. When plotting shear stiffness to penetration resistance ratios using existing frameworks, what we can see is that sands involving different cementation levels can be effectively tracked using this Kg parameter, and that this Kg parameter increases due to added cementation. Furthermore, we can see that really highly biocemented sands have Kg values that exceed the 1100 value that was used in the original framework, most likely because of the presence of higher cementation in these experiments than those accounted for in the original database of natural cemented soil deposits. And with that, thank you for your attention. I'm going to turn it back over to Jason DeJong, who will cover experimental and numerical aspects.
So continuing on and now looking at the implications of this with respect to engineering behavior. And we've integrated two separate sections in the paper, the experimental and the numerical part together for conciseness here. We'll begin by looking at the small strain response and particularly some resonant column tests. Remember in recalling that shear wave velocity was essentially proportional to the fraction of calcite. You're going to see us start talking about improvement level as in terms of delta Vs as our target. So the top set of figures shows your shear modulus as well as your normalized shear modulus versus shear strain on the horizontal axis, and there's a number of observations that we can make. First of all, and as expected, you see with the higher cementation level, you begin at a higher shear modulus, but all those degradation curves collapse down and essentially converge at approximately 0.5% shear strain. The normalized shear modulus curves show us an expected and systematic shift to the left and downwards, and indicating and reflecting the fact that the threshold shear strain goes to smaller and smaller strain levels. This corresponds obviously then with an increase in the damping that occurs at those small strain levels because of the degradation of the cementation. We can go to slightly higher strain levels and begin by looking at miniature triaxial tests performed with concurrent CT scanning at particular strain intervals. The results shown in the middle in blue are for a 5% cemented calcite specimen. The red shows an uncemented specimen, and you can see some clear differences in the global response. First of all, increased stiffness, increased peak strength, and also a post-peak softening towards a critical state value, which is similar to the uncemented sand case. We can interrogate and evaluate the CT scans, and we can identify how this failure mechanism changes due to the cementation level. So for example, in looking at the blue boxes, highlighting a series of images with respect to porosity and incremental strain, we can see from these results, as well as other results in literature, that the shear bending begins to occur at a smaller and smaller strain level as cementation increases. And interesting, the shear band thickness decreases down to about 5 particle diameters. So it becomes pretty narrowed and complex. We can interrogate this further, actually, by leveraging discrete element modeling results, particularly in simulations such as this one, where we're modeling both the sand particles as well as much smaller particles representing the calcite crystals that bind these particles together. You can see in the center image that for a variety of cementation levels, we can get agreement between the stress-strain behavior, essentially. And then we can interrogate in the DEM further, and I'm showing results just for the 5% calcite content on the right axis. On the right set of figures. And we can see, first of all, that we get rapid load transfer from the soil to the cementation binding particles, which results in the failure or degradation of those bonds captured as a bond breakage percentage in the top right plot, most of that occurring within about 1 or 2% shear strain. As shearing continues, you can see the coordination numbers really decreasing for the sand particles because of the breakage of those cementation levels. We can extend these results from small strain triaxial to the normal size triaxial tests, and that's covered in the paper. But we can also move over to DSS testing and take a look at results there. So in this case, we're looking at drained and undrained response from monotonic DSS tests. Improvement levels are from 0 to 500 meters per second. The stronger improved soils is in the darker lines. And again, we see the same type of behavior. That is increased stiffness, much stronger or higher peak strength. And for the drain case, we see a very strong dilative tendency. In the complement of undrained tests, we see the shear stress obviously increasing as well, but now we see very strong generation of negative excess pore pressures due to the dilative tendencies of these kinds of materials. I'll note that the benefits of cementation may decrease somewhat at higher strain levels because of the degradation of that cementation. So moving from monotonic towards cyclic because of the interest in dynamic response, we can see two examples of results shown here, both with a CSR of 0.2. The upper set of figures is for the uncemented case. The set of figures in the middle is for a 100 meter per second increase. So a very modest increase in the cementation level. But you can see the number of cycles required to liquefy the material becomes substantially larger. We'll replace those bottom two sets of figures with ones at much higher CSR levels, 75.75 and 1.5, with corresponding shear wave velocity improvements of about 200 and 400 meters per second. And the number one observation from this is really the number of cycles required to degrade those bonds in order to generate strain accumulation goes up substantially. And that's the primary benefit realized. Once we have started generating strains, the rate of excess pore pressure generation becomes pretty complementary to uncemented sands at the levels of cementation we're looking at. But the net result is that the number of cycles required to achieve 3% single amplitude shear strain goes up. In addition, the post-triggering strain accumulation also decreases. We can compile this data in a couple different ways, a little bit more complexly. And the figure you're looking at in the middle is change in shear wave velocity on the x-axis, or an increment of improvement, versus the number of cycles required for 3% shear strain for different cyclic loads. So it becomes, you can see very clear advantages of substantial number of cycles of benefit that are gained, even at small cementation levels. We can push this a bit further and look at CRR curves on the right-hand figure. And where the vertical line is, that indicates that for a 10% cycles, you get a CRR increase from about 0.1 to 0.3 with a pretty modest increase in cementation levels. There's substantial gains being realized here with respect to liquefaction resistance. I'll also note that the post-cyclic reconsolidation strains benefit from the cementation as well, particularly for improvements above about 200 meters per second. So we're seeing improvements with respect to soil behavior across the board, monotonically and cyclically. So in addition to the experimental work, we also have the desire to model this and to capture this in our constitutive models. So there's a number of models that have been developed for cementation. I'll highlight the modification to the PM4 sand model, which was discussed this morning. And there's the NC term is to highlight the ability to capture effects of cementation. Now that model has a few modifications to it to incorporate these effects. Number one, there's an addition of a tensile strength component that captures that cementation. In addition, the magnitude and stress dependency of the shear stiffness becomes dependent on the cementation level that you have achieved. In addition to this, the cementation damage is tracked through the plastic deviatoric strains. And importantly, once the cementation has degraded, this defaults back to the uncemented model. And that reflects the developer's assumption that we are dealing with cemented soils, but they are still, in fact, soil material, which can be appropriately modeled as such. And we're not dealing with rock-like material yet. This is one example of the results of how of the agreements that can be achieved, with the experimental results in the darker color and the simulations in the lighter color. Typical protocols for this would be first calibrating to the uncemented sand response, and then adding in and calibrating the additional parameters for the PM4 sand C model. So there is ongoing development of this and calibration against a much broader range of conditions, including those expected in future field trials. So given that observed improvement at the element behavior, let's turn and take a look at what efforts have been made with respect to upscaling. Review of both the 30 or so different projects that have been performed by people around the world in trying to upscale this process in combination with the existing kind of design methodologies for existing ground improvement methods. We've kind of seen this kind of flow chart fall out from the approaches that people have made. And so just to walk through this briefly, the first part, obviously, is just a preliminary suitability evaluation, as that's a screening stage of evaluating how suitable MICP might be, considering the soil conditions, the expected loading, and what the performance requirements might be. From there, there'll be some site-specific evaluations, particularly with respect to the environmental and the geologic conditions, including pilot laboratory tests to ensure effectiveness of the MICP technology. We move on to site characterization and recognizing that we'll be injecting and creating a localized flow regime for treatment. We need to have a proper 3D model with respect to the hydraulics and the geomechanics. And then from here, and from these results, we then be trying to identify our targets for how much soil improvement we need. What's our target shear wave velocity improvement, for example? We deal with the logistics of the implementation, at this point identifying the well spacing, the establishment and the mixing and the injection of the treatment solutions, et cetera. And then very importantly, establishing our baseline conditions at the site, our strategy for how we're going to monitor improvement throughout that treatment process, and then at the end, verifying our post-treatment condition. On top of this, and particularly because of shear wave velocity, there's a potential to do health monitoring of MICP in the longer term if the sensing technology is established up front. So we're going to look at two different aspects of upscaling. First of all, I know you can't read this, but this is the list which is in the paper of all the different projects that have been performed by various researchers who have tried to upscale this technology beyond a 0.5 to 1 meter or so. And so in summary from this, there's been about 25 different methods, and they have a wide range of characteristics in terms of if it's a synthetically built model, if it was performed in situ, what the flow geometry may have been, the dimensions, the volumes, the depth of treatment, the soil types that have been treated, whether it's been augmentation or stimulation. A lot of the early work was augmentation, and now it seems to be transitioning or more balanced with respect to stimulation. And then finally, the range of applications. But what we can take away from this and from these types of observations is we are getting to the larger scales, and we've been able to carry some of this knowledge and understanding that we developed at smaller scales towards the field scale. And so we'll just briefly give you a representative example of this, which kind of holds the complement of all the monitoring methods as well as upscaling. And so this meter scale or 4 meter scale upscaling project had many different objectives, including demonstrating the efficacy of biostimulation in natural soils, controlling that treatment uniformity, optimizing the treatment formula, demonstrating the monitoring abilities, and the byproduct removal. So you're looking at 4 meter long columns prepared with naturally alluvial soils. All of the columns were subject to the same 3 steps that Mike had talked about: enrichment, cementation, and byproduct removal. You can see the time course of treatment for this project was about 25 days or so, which is maybe representative of what we expect to occur in the field. And there's 3 different comparisons we're going to make. You can see stimulation low, which is essentially a low reaction time or a slow gel time. Stimulation high, which is a faster reaction time but using native species. And finally, injection of a relatively large volume of active bacteria at the injection front through augmentation. So we'll look through these results and try to tie together how they are integrated and connected with each other. First of all, looking at the microbiology or the cell density and the geochemistry or the urea, you can see in the top set of plots, aqueous cell density. And you can see this for the stimulation low plots in light blue, that across the board, throughout the testing program, the concentration of the bacteria remained relatively stable and relatively uniform, and smaller and lower than the other treatment conditions at different points in time. The lower set of urea are time courses for 1 injection, and what we're looking at here or looking for is a systematic reduction as uniformly as possible across the length of the cell. That's indicating that we're getting pretty uniform cementation or precipitation occurring. So that looks favorable for the stimulation low case. We've talked about the strong coupling between shear wave velocity and calcite content. The top set of figures is showing from dark to light improvement in cementation as reflected by shear wave velocity. So the left set of figures you can see is most uniform in terms of the shear wave velocity increasing throughout the treatment course, whereas the far right set of figures, you can see that cementation was primarily localized near the injection ports. The bottom plot now carries down the final shear wave velocity contours, but plots onto it with a differential vertical axis the final measured calcite content. And I think you can see for all 3 cases, the strong agreement between the colored trend lines and the data symbols indicate the strong correlation between shear wave velocity and calcite content. Again, providing us confidence in VS being able to help us monitor the progress in real time. The final one is byproduct removal, and this is the final step through the treatment process, and you can see in this case, systematic reductions or lowering of the contours of the ammonium, and that also corresponds to reductions of the sorbed ammonium as well to pretty low levels. The second part of the upscaling is not the treatment method, but is upscaling to ask, how might this improve different geotechnical engineering systems? And so in this case, we're going to look at the question of how MICP could, at the systems level, improve resistance to liquefaction triggering and also reduce the consequences if liquefaction triggering occurs. So there's a summary of the different plots or different projects that have been performed, but a vast majority of these have been performed using the centrifuge because of its scaling capabilities. And so in this case, the 1 meter centrifuge at UC Davis was used to quantify the increase in cyclic resistance to triggering, to map how cementation degrades over multiple earthquake shaking events, to track pore pressures and shear strains, and to assess the applicability of existing triggering curves. And so just a simple cross-section of the model on the right-hand side, you can see it's relatively simple level ground condition. Under 80 G, this is simulating about a 10-meter deep, loose liquefiable deposit. There was a host of different tests performed, but we're just going to take a look at two today for simplicity. One being the uncemented case, or the existing ground conditions, and the second being for improvement to about 325 meters per second increase. The various measurement systems allowed us to make two types of observations. The first is the discrete sensors allowed us to monitor the performance during the shaking event. And the second is that the shear wave velocity and cone tip resistance could provide measures in between or after particular shaking events, much like we do with our case histories in the field. So this allowed us for a series of analysis and time series, and from there, in addition to that, the shaking level was systematically increased. So these were somewhat complex and long tests, and you can see on the horizontal axis is simply the number of shaking events for a given model. So it was quite a few, but I just want to grab out and highlight 2 points here. First of all, I want to note the uncemented characteristics are in the triangles, and the moderately cemented conditions are in the blue circles. The uncemented model liquefied with only about 0.06 G shaking, and as we would expect, without cementation, the shear wave velocity didn't really change before or after shaking, and this has been commonly observed. On the other hand, the moderately cemented material did not liquefy until about a shake of about 0.17 G, and on top of that, we could also see from shear wave velocity that there was some damage to the cementation and it began to degrade. So we'll just grab those two events, the 0.06 event and the 0.17 event, and compare them in the same figure, and you can see that right here. The maximum CSR felt in the upper portion of that soil was 0.15 for the uncemented case, but it was up to about 0.8 for the cemented cemented case. And we can, in looking at the data in a little bit more detail, you can see that the cementation reduces the rate of excess pore pressure generation as well as the rate of strain generation. And it also, on the other hand, does amplify the accelerations at the ground surface a bit. So that's something we'd have to consider if we provide this kind of improvement. We also have been able to do some 1D modeling with PM4C in order to simulate this same response. And in this case, the shear wave velocities measured in the centrifuge were used to calibrate the numerical model. And on top of that, the input-based motion from the centrifuge test was the input-based motion for the numerical model. And so results are shown here on the left for the uncemented case, with the experimental results being in the dark line. And on the right-hand side, it's actually inverted. The experimental results are in the lighter line. But in both cases, we can see that particularly up to liquefaction triggering, we can get pretty good agreement with respect to the centrifuge data as well as the numerical simulations and the combination of those. There's one further step, and that's taking a look at cone tip resistance, because cone tip resistance many times is the deciding factor for assessing the level of ground improvement. And so let's take a look at that a bit more closely. The plot you see on the right-hand side is for the uncemented case. And here, the initial profile is shown in the blue line on the left-hand side. Over the course of about 14 shaking events, the earthquake motion systematically densified the soil, and we saw a corresponding increase in the cone tip resistance. going from about 2.5 to 5 MPa or so. On the other hand, the biocemented material had initial cone tip resistance shown on the right-hand side. That is a cone tip resistance with about 10 MPa. Following liquefaction, that cementation degraded somewhat, and the cone tip tracked that. It decreased a little bit initially, but then with further shaking, even as the cementation is being damaged to a certain extent, it also starts to densify, and as a result, the cone tip resistance goes up. So collectively, we have tracking of shear wave velocity, we have tracking of the dynamics, we have tracking of cone tip resistance, and we can stitch these together, and we can look at them in the context of a common liquefaction triggering curve with the Boulanger and Idris. And so the plot you're seeing here on the right-hand side, that triggering curve is normalized or shifted for a mean effective stress of 35 kPa, which is the stress in the middle of our model. So we're using stress-normalized cone tip, and we've computed equivalent cycles for the motion following seed. The series of gray arrows shows you essentially the walk, if you will, of the moderately cemented material. And you can see going up from the kind of in the middle and the bottom upwards, those series of open symbols are all cases where this material and this model did not liquefy. And it's only at that very large shaking event where the cone tip resistance shifts to the left a little bit do you start seeing liquefaction. And you have another liquefaction event slightly above that one. And then we dropped the loading level down to the very small levels and repeated the process. But in total, if you collect that information with that from the heavily cemented model and a lightly cemented model, the two other data sets shown here, you could observe that there is a kind of a shift or a clear persistent benefit from the biocementation with respect to liquefaction triggering. So that's encouraging at the systems level, being able to demonstrate what that improvement can be. So just let me wrap up and try to tie together the breadth of what we just walked through in the last hour or so and draw a few conclusions. First of all, I hope you've seen and come to appreciate that bio-inspired and bio-mediated processes, as exemplified by our deep dive into MICP, can present some unique opportunities to develop new technologies that hopefully can lead to step changes in our practice. We have developed a pretty robust, I believe, understanding of the underlying biogeochemical processes, and that these are effective and can be applied to a range of different materials. This allows for optimization and control of the cementation. Monitoring is key, and our ability to monitor the microbiological, geochemical, and mechanical changes in real time and also at the end are really important for tracking the progress and also to support the parallel modeling. We've realized significant improvements in engineering behavior across the host of different parameters and attributes that we've talked through. We've seen the benefit of numerical simulations, discrete element modeling, revealing some of the mechanisms of failure, and the continuum models, constitutive models with continuum modeling, allowing us to start modeling this more and more at a systems level and hopefully support us as we go to the field. We've looked at upscaling of the treatment methodology itself, and while we have some ways to go, you can see that we are gaining control of treatment uniformity, optimization, minimizing material use, being able to monitor it, and manage the byproducts reasonably. For centrifuge modeling, that's been helpful for us to demonstrate, I believe, the potential use of this for the liquefaction triggering program and effort. And finally, we have continued work, obviously, but we believe that both continued fundamental studies in parallel with a push for some rigorous upscaling field applications will lead this so that we will begin to see more and more MICP technologies being demonstrated and then hopefully adopted at the field scale. So as I wrap up, I just want to again recognize and thank the organizers, their persistence and tenacity in putting this event on, particularly with all the complexities in COVID. Everything else is tremendous. We just also appreciate the opportunity to communicate this with you. So thank you very much for your attention.